Okay, students, good afternoon. Sorry we're starting a little bit late. Hopefully they still haven't got this display thing figured out up here. Um, just one small announcement before we start talking about uniform circular motion, and that is if you were not here Tuesday, and if you did not pick up your printout from exam two, excuse me, from exam one, I have them. They're over in my office, and you can pick it up after class. We'll just walk over to my office. If you can't make it today, you got to jam out of here for your next class. We'll try to catch you next Tuesday. Colin. Your guys is Darian figured it out, and I just haven't entered them into the computer into the grade book yet. So you will be squared away probably this afternoon when I get to it. If you can come, do you have to go to class right after this? Come on over and I'll show you what we got. All right. Last time we were talking about the Nardo Ring, the circular test track, and the boot heel of Italy. As an excellent example, real life stuff that you can see. Well, if you're in Italy, you can see it. Real life stuff that you can see of everyday things that are in uniform circular motion. And so let's take a look at some of the things that led up to that. We'll just do a little review here from a recap from last time. We took a general curve, kind of any shape, not a circle, and we drew in this imaginary circle that's tangent to the actual path. And the whole idea of that is that for just a few inches or a few centimeters or a few miles, whatever the size of the track is, you're actually close to the physical track if you're on that circle. In the math department, they would use the phrase infinitesimally close to the path, or an infinitesimally small neighborhood of the track. If you've had calculus class, raise your hand if you've had calculus, just to show of hands. Okay, so you may have heard that word infinitesimal neighborhood before. But for us, we're just going to refer to it as, for a few centimeters, a few meters, a few miles, we're close enough for government work when in approximating the track as a perfect circle. Now, the radius of that circle goes from the center out to the path, and that particular radius, which I have featured in blue here or emphasized in blue, that's the key radius of all the zillions of radii you could draw in for that circle. That's the one that helps us figure out, the curvature. The length of that radius, the length of that blue line segment, is the radius of curvature for the track at that point. And as I mentioned last time, if you go a little further down the track, you might have a different radius of curvature. You might have a different center of curvature, but you will have one, however big or small it is, wherever the center may be. Also, that particular line segment can be used as a position vector. So here I've sketched it in red as an arrow from the center toward the point in question on the track. Now, relative to the center of the circle, that is the position vector. And it is perpendicular to the velocity, but only to that at that point, the velocity at that point. As I said, if you go a little bit further down the track, you're talking about a different circle, maybe a different velocity, maybe a different speed. Whatever you're doing on the track, this only holds for this particular point. But you can do this at any point you want. So it's always something that you can do geometrically. The position vector is customarily labeled many times as R with an arrow over the top, or boldface R, as I have in my outline, 2B. That is perpendicular to the velocity. And let's keep going. The velocity vector is tangent to the path, and it's perpendicular to that radius vector. And for that reason, the acceleration is going to be perpendicular to the velocity, but the acceleration, delta v, is inward toward the center of the circle. So now I've traced it in, and you do what you think is good on your notebook. I've traced it in as a blue arrow toward the center. Don't make it going outward from the center. The position vector, yes. That red one, yes. But this one is the acceleration, and we know that delta v, if you're turning right, your delta v is off your right shoulder. All right, so for this guy, it's as if he's making a right-hand turn on a circle. So the center of curvature is off to his right, and the acceleration is off to his right. It points off to his right. The customary symbol for that, we've seen it before, is A. And so that acceleration, it's pretty important. The acceleration is perpendicular to the velocity and toward the center of the imaginary circle. Now, part 4 is for uniform circular motion. All right, now on a general curve, you might be changing speed or something like that. But in uniform circular motion, your speed doesn't change, but your delta v is changing. Your v's and your delta v's are changing. But the delta v is always pointing toward the center. It's perpendicular to the velocity because it neither speeds up nor slows down anything. Because that is true, the force is also directed toward the center. Now, the fancy vocabulary term we use for that is centripetal. C-E-N-T-R-I-P-E-T-A-L. Centripetal. And what that means is, if you read the textbook, I do a little breakdown of the Latin root words. Centri means center, of course. And then petal comes from the Latin word to seek or to go towards. And so this means an arrow that is aimed toward the center. I want you to write another vocabulary term. It's slightly similar. This second vocabulary term, Akin, I have your paper for you. Did you see the change? I changed it. Okay. Yeah. The second vocabulary term is centrifugal. C-E-N-T-R-I-F-U-G-A-L. Centrifugal. Centrifugal. Now, you've probably heard that a lot more than you've heard centripetal. But centrifugal is a vocabulary term. C-E-N-T-R-I-F-U-G-A-L. Raise your hand if you've got it written down in your notes. Did you get it? Okay. That's most of you. Okay, if you've got it written down in your notes, cross it out now. Because we're never going to use that. Centrifugal. See, I got you guys napping. You thought I was some new concept. Centrifugal. Fugal. Fugitive. Means to flee. So centrifugal is an adjective that means something's pointing away from the center. So we're never going to talk about centrifugal forces. That's like a misnomer. That's like saying misunderestimate or internets or something like that. You know, centrifugal as a colloquial term is not a good, for us, it's not going to be ever used. So cross it out. Because our stuff, what we're interested in is the stuff that's pointing toward the center and toward the center of curvature. All right, so a little bit of a head fake there to centrifugal, and then we're moving away from it now. We crossed it out. We're moving the other direction. Now, last time we talked about the Nardo Ring, and let's go through the specs for the Nardo Ring. And this is a view from space. It's from Google Maps. The outermost lane of the Nardo Ring is banked at a certain angle, and in that decision they optimized it for 149 miles per hour. And if you drive at that speed, you don't actually have to turn the steering wheel left or right. You'll stay on it if you stay at the speed. Now if you change your speed up or down below 49 or 149, excuse me, then yeah, you'll have to do a little steering. I mean, you still stay on the track, but it's not as efficient. So they built this. Now this is 149, so they're testing out like race cars and stuff that go at that speed. Okay, so, and in Italy they have some great race cars. Ferrari, they're some of the best. Right, so they test them out in that outermost ring. So if you change the speed faster or slower, you crank the steering wheel a few degrees to stay on the track. Now the innermost lane is for testing trucks and passenger cars and stuff. You know, something that your mom would want you to drive. You know, your mom's always concerned about your safety, and you know, oh, my little baby at school. You know, we gotta give him a good car. And raise your hand if your mom gave you a really nice car before you came up here. See, hardly any hands, just a few. Anyways, that's the way moms are supposed to behave. I guess I never got one from my mom or my dad, but. So anyways, 50 miles an hour, that's optimal speed for a passenger car, a truck, or something like that. You know, so a big 18-wheeler, yeah, that's the speed they drive on the Autobahn up in Germany. The interstate highway here, if they're not going through Orlando, that is. Hey, raise your hand if you drive on the interstate on I-4 to come or go to class. So is it going through Orlando? Is it a total nightmare right now? Yeah, I've never seen such bad road design as through here in Orlando. It's amazing. All right, so that's the Nardo Ring. So the equations that we're going to do, you can think of us as doing or figuring out, deriving an equation for a truck or a Ferrari on the outer ring at Nardo. And they put the cruise control on and they just go around the circle. And what we're going to do is study their velocity and position. So let's go to do that now. Okay, we're in uniform circular motion. That means you're on a circle. You're moving at constant speed, i.e. Cruise control is set. And we're going to study two different instances of time. So here's a snapshot of the track. You know, I can't see where I can't use my cursor today because I can't see over here where my cursor is, but I'll try to verbally describe where my cursor should be. This circle on the left of the screen is a snapshot of the system at Nardo at some time t1. Now the radius position vector is rightward from the center, and for that reason, if the car is going anti-clockwise, which I believe is what they do over there in Italy, on that track anyways, then the velocity vector will be straight up if the position vector is right there at the 3 o'clock position. Now a little bit later, let's say that we take another snapshot and you're about 30 degrees up the track. So now you're at about 2 o'clock. Position-wise, your black position vector on this second circle on the right side of the screen is now tilted up towards the 2 o'clock position. And your velocity vector has now tilted to the left, anti-clockwise, by 30 degrees in this diagram. But it's uniform circular motion, so you have the same speed. So label both of them V and V. It's a circle, so label the radii R and R. Right? Now we're going to use those equalities, radius equals radius, speed equals speed, to figure out an expression for the centripetal acceleration. And the way that we're going to do that is by taking the two snapshots, and we're going to kind of break them apart. You know, I'm going to see if I can push this forward here. Let's see if this will work. I've got to see. I've got to be able to see. Oh man, this is pitiful. Let's see if I can get this. All right. So here we go. All right. So what we're going to do, we're going to copy the two radii, the two position vectors. Here we go. Okay. Here we're going to copy them tail to tail. So here's the first one, and all right. So there's the other one. And so so let's park it down here in the lower left. All right. So what we've done is we've copied the two position vectors, tail to tail, and kind of off to the side. So we've broken apart our two snapshots. We've analyzed them. That's what analyze means, to break apart. And we've reassembled it into this kind of V-shaped structure here. Now we're going to do the same thing with the velocity arrows, the red ones, right? So here's a velocity arrow, and here's a velocity arrow. And so what we're going to do is take the velocities, and we're just going to kind of copy them, and then park them up here to the upper right. But you park them wherever you want. I mean, wherever you have room on your notebook paper is good. All right. Now let me move those two snapshots out to the side here, and here's a blow up of my two vector combos. My position vector combo down here in the lower left, and my velocity combo up here. Now, nothing's too bodacious about this. It's just a pair of position vectors tail to tail. But now what I want you to do is connect the dots just like this. Go ahead and connect those dots. And I made a dashed line. And now we've got a triangle for the positions. So we'll call this the position triangle in black. And you can make a note of that off to the side somewhere. Position triangle. And let's put in the radii. You know, the two long sides of this triangle are R and R. And the baseline is, or that dashed line, the base of the isosceles triangle, is the approximate distance that you have traveled on the Nardo Ring. Now I emphasize the word approximate because it is not exact. It is a straight line, and the track is actually a curve. So the actual mileage that you go on the track is going to be a little bit more than the mileage of this straight line. So your track, you might go 200 meters on the track and only 199 on this line segment. But they're going to be pretty close. And the closer we put our two instants of time together, the closer and closer they get. The better and better the approximation gets. But for 30 degrees, it's still pretty good. All right? Now, let's put in the same maneuver on the velocities and form a velocity triangle up here. So connect tip to tip. And the isosceles sides are V and V. But let me ask you a question. And I want you to think. So this is kind of a mental IQ test question. And if you're bold, you can answer, you can raise your hand and propose an answer. And I will tell you if you're correct or not. What is that red dashed line, the base of the isosceles velocity triangle? What should we call that? I see one hand up here. Hold on. Anybody else? Think. What should we call that? Caitlin, any ideas back there? Okay. What do you think? Approximate speed? Incorrect. That's good over here. Approximate distance, yeah. For the position triangle. tip to tip of two velocities, first velocity and then the second velocity? What do you think? Time and O. It is not the time. It's got to be, it's a velocity triangle. So what kind of a... What do you think? Acceleration? Oh boy, you are warm. You are burning up. But it's not an acceleration because these are velocities. What do you think back there? Delta V, and delta V forms the acceleration. Okay, so you're right on it, and he's on top of it. That is delta V. So go ahead and label that as delta V. And now what's your name again over here? Colin. Okay, Colin. That is going to become our acceleration. You'll see it in a minute. Okay, but technically, yes, that's a delta V vector. All right. Now, these two triangles, they're both, the sharp angle is 30 and 30. If it's uniform circular motion. And if I go 30 degrees, a 12th of the circle, then the velocities have tilted 30 degrees as well. So we got 30 and 30. And the sides are proportional. Now, you cannot say that the sides are equal, because they're not. I mean, they look equal here in this picture, or close to equal. But no, they're not equal. And the reason for that is one is a triangle that is measured in centimeters, the position triangle, or meters, or light years, or whatever you're working with. The other one is measured in meters per second, in speeds. Okay, so you can't mix apples and oranges. Okay, your mom was right about that. All right, but that's all right because we are going to use those triangles as proportionality or as proportional triangles and work a proportion and get an expression for acceleration. Now, before we do that, let me just add this comment. This approximate distance is V delta t. It's approximately V delta t. Okay, now V is the speed that this thing's motoring around the track. So distance is speed times time. Now I want you to add that in there as well, so that's V times delta t. Now up here in the middle of the screen is the proportion that we're going to use. And this proportion is the key that locks in all the centripetal acceleration formulas. Now, Valeria, what we're going to do here is look at the first ratio, and that's this one. Those are the isosceles sides. Okay, the isosceles side of the position triangle on the top, and in the denominator, the isosceles side of the velocity triangle. Okay, so this is position over speed. Position triangle over velocity triangle. And in specific terms, it is the isosceles sides. So that's the ratio. Okay. Now, over here, this term, the second term, the right-hand side of this proportion, Omari, is the base of the position triangle on the top, V delta t, and the base of the velocity triangle, delta V. All right? And so that, if you look at that, do you see, Colin, do you see acceleration in there anywhere? What do you see? Yeah, we got velocity and we got a delta t, but they're upside down. It's not. It's the flip flop of the acceleration. See right in here, right in here, delta v on the denominator. But for an acceleration, that should be in the numerator. It's okay. We'll just flip flop it. How about that? So we'll flip flop it, and we'll also move. We'll cross multiply. Let me see if I can point it out. This extra v, this factor of v over by the delta t, we'll cross multiply that over to the bottom and get a v squared, so r over v squared, and then we'll flip flop it. And here's what you get. Donna, donna, donna. I wonder if they transcribed that. Delta v over delta t. There it is. Boom, there it is. Delta v over delta t, acceleration. And then here's your leftovers. V squared over r in this equation on the lower right of the screen. And the right side of that equation is v squared over r. And so what that tells you is, all right, there is my centripetal acceleration. V squared over r. Colin. Colin at the aisle. Well, Colin, what I did was I started with, see, this is geometry class up here in the upper right. That's just long sides ratio. And then over here, this is the base, the ratio of the bases. So the base of the position triangle is here, and it's the numerator here. And the base of the velocity triangle is here, and it's down here in the denominator. Okay. Now the isosceles sides, the long sides, are r for the position triangle. That's up here, and v for the velocity triangle. That's down here in the denominator. So theoretically, the ratio of corresponding sides, no matter what pair of corresponding sides you take, they should be equal. Okay, they should be proportional. Okay, that's what proportionality allows you to do. So geometry class gives us this, and then a little bit of insight allows you to isolate delta v over delta t and get yourself an acceleration. And so my next slide indicates that because we have proportional triangles, and look, just keep thinking it over, man. You know, if you're a little rusty on your proportional triangles, it's all right. You can read it up on the internet or something like that. Because of proportional triangles, i.e. the speed triangle being proportional to position triangle, we're allowed to say this. The centripetal acceleration is v squared over r, and that's a with a subscript of c for centripetal. Never centrifugal. If you see me write centrifugal on the test, that's like a Chuck Norris option. It's never going to be the answer on the test. Now, Chuck Norris is the answer outside of this classroom. But anyways, centrifugal, no. Centripetal, yes. And here's a centripetal force formula. This is F equals ma. You know, Newton said any force that produces an acceleration is going to fit the form F equals ma. All right. So if you have an object of mass that's, you know, on a circle, you know, like a spacecraft orbiting Earth, all right, that spacecraft is going to be a few tons, you know, a good sized one, more than that for a big one. So it's going to have a mass. And so the centripetal force in newtons would be calculated this way. M times v squared over r. So those are the two formulas for centripetal acceleration and centripetal force. And I tend to think in terms of centripetal acceleration a little bit more than centripetal force, but we're going to do an example here of centripetal acceleration concepts that the star pupil of Galileo came up with. The star pupil of Galileo was Sir Isaac Newton. And what he did was leverage these centripetal acceleration concepts into figuring out the theory of universal gravitation. So let's take a look at what he worked with. First of all, they had a fairly decent measurement of terrestrial acceleration and free fall, i.e. the legendary apple falling from the apple tree. And they get that from distances and time measurements, and we've done that. In metric system, it's 9.8 meters per second squared. I believe in English, it would be 32 feet per second squared. So he probably was thinking 32 feet per second squared. But we're going to think in metric terms. So he could figure that out, and many other people were able to figure that out as well. Now, the moon, he knew that the moon was on a circular orbit. And they'd been able to figure that out for probably close to 100 years by the time Newton rose. Did you know that Newton and Galileo died the same year that Newton was born? It's kind of interesting. So Newton knew that the moon was on a circular path, and therefore the centripetal acceleration concept would apply. Something had to supply some newtons of force on the moon. And his idea was, I think it might actually be gravity, the same thing that pulls that apple straight down towards the Earth. For the moon, it makes a circular orbit. Now, they knew the distance to the moon as a multiple of Earth's diameter. And they knew the Earth's diameter, not to the nearest centimeter like we do now, but they had a pretty good estimate of it. And so he was able to figure out, also knowing the orbital time, 27.3 days for one full circular orbit, he was able to figure out the moon's centripetal acceleration. Now, before we get into the nitty-gritty of that, I have a clicker question for you. All right, so turn on your clickers. For those of you that are using your clicker for the first time, if you are, no problem. Just hold the power button down until you get the flashing square, and then type B, and you'll be on my frequency. And then you'll get a message that says go nitro, and then ready. And when you get that, you're ready to roll. So let's try a real cinchy question here. And they're going to get harder, so don't get complacent. Question 1 for today. What is the value of 60 squared? So try not to be scared off by these two ferocious guard dogs. The reason I use pictures from Reddit a lot is because sometimes my questions, they don't really need a diagram, but I don't want to have a totally blank page, so I just find something I like from Reddit. Like these two killer dogs, killer chihuahuas. 30 seconds. Some of the stuff you see in Reddit, oh my goodness. And I only look at a few Reddits, but 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah. Whoa, 100% geniuses. Sweet. Okay, now we're going to be doing another clicker question here in a second. But let's get back to gravitation. And let me get this thing out of the way. And let me get my clicker back up here. Okay, so this is part 3 of our outline. We're still, talking about G and so forth. And unfortunately, I forgot to take out the closed caption rectangle before class. Sorry about that, you guys. It might distract you, but it won't take anything away from lecture. So the Newton said, all right, something is accelerating it. It's on a circular path, so it is accelerating. And he was thinking that it had to be gravitational free fall. And instead of going straight down to the Earth, it's got some sideways velocity, just enough to keep it on a perfectly circular, so it doesn't come down like a baseball in a parabolic arc. Thank God, because we don't want the moon crashing into the Earth. But it's fast enough to just go all the way around and perfectly lap itself on a circular orbit. And so he was able to estimate the acceleration 0.027 meters per second per second. Now, compared to the gravitational acceleration at the surface of Earth, g, which is 9.8 meters per second squared, this was about 1/3600th of Earth's surface gravity. So the moon's got a circular path. It's getting some delta V, so it's getting some acceleration. And if you work it out, it's about 0.027 meters per second squared. And that's about 3,600 times smaller than good old 9.8 meters per second squared here on the surface of the Earth. Now, here's the other cool thing that he noticed. He knew the radius of the Earth was about 1/60th of the total distance of the moon. So, here's the distance to the moon, and the Earth's radius is about 1/60th of that. Okay, so from the center of the Earth to the moon is about 60 times farther than from the center of Earth to Orlando. Now, I took this diagram here, a little picture of Earth and a picture of the moon, and here's two little blue vectors to represent the small vector. It's pointing like from the center of the Earth to about Cape Town, South Africa, somewhere around there. That's this little guy right here, almost horizontal. And then this one has some dots in it pointing toward the center of the moon. And the idea is that from the Earth to the center of the Earth to the center of the moon, it's about 60 times more than from the center of the Earth to Orlando. All right? And so you might ask yourself, well, is that a coincidence? Because 60 squared is 3,600. So, so Sir Isaac Newton said, I do not think it is a coincidence. Now, here's another look at the same data. This picture, by the way, here's Earth all the way down here on the lower left. And here's the moon up here in the upper right, that little circle up there. And this diagram is rendered to scale, diameter for diameter, also distance to scale. So if you were out in space on your way to Mars and you looked back at Earth from a certain distance, they would look like this. If you look in like a textbook or an encyclopedia or something, or the internet, a lot of times they'll show the Earth here and the moon, maybe the right size, but, really close. It's not 60 times further away. It's right up, one diameter away maybe. And we definitely do not have that. But this is the truth. So try to draw this sketch, do your best, because this is the true proportions for the Earth-Moon system. Now, if you consider the distance from the center of the Earth to the surface of the Earth, if that's 1 unit of distance, then it turns out that the distance to the center of the moon is about 60.3. So it's pretty close to 60. Similarly, acceleration-wise, if you think in terms of 1 unit of acceleration, or actually what you could call 1g. If g is your unit of acceleration, then the moon's centripetal acceleration due to gravity from Earth itself, according to Sir Isaac Newton, is about 1 over 3,599.6. And that's pretty darn close to 3,600. So guessing that this is 1 over 60 squared is not an outrageous conjecture, because there's a lot of plus or minus, there's a lot of give and take in the measurements. You know, he didn't have to the nearest centimeter for any of his distances. Not for the size of the Earth, not for the size of the moon, and not for the distance to the moon. But he had enough to see this pattern. And so this question naturally arose. Does the gravitational force depend on 1 over the distance squared? So whatever the distance is, square it, and that is how the gravitational force gets weaker. So that was a question that would, you know, probably arise in anyone's mind if they look at these numbers. And it appears that Sir Isaac Newton did make that conjecture, that it was dependent on the distance in this manner. Now let's go to number 6 in our notes, and let's put it all together. This is going to be his law of universal gravitation. Statement 1, or statement A. It depends on 2 and only 2 physical factors: the mass of each object in kilograms and their distance in meters. And you're actually going to square the distance. But you measure it in meters, and then you go to your calculator and square it. And he said it has to behave in this way, that the more mass you have, the more force. So whatever else happens, the mass has to be up in the numerator if there's a fraction. Can't be in the denominator. But he then said, all right, if there's more distance, the force is going to be weaker. So yeah, the distance does have to be in the denominator. And this is the form that he worked out, and it's been very well verified. G times m1 times m2 over r squared. m1 is the mass of one object. m2 is the mass of the other object. And the product of them, excuse me, I need some coffee. The product of m1 and m2, that goes in the numerator. The distance is r between those two objects. That goes in the denominator and is squared. So that's actually r squared in the denominator. Now the factor of capital G at the top, go ahead and make a little teeny note about that. That is known as Newton's constant, or the gravitational constant. It is a constant of nature. It is like a conversion factor that you have used, for instance, when you convert from Fahrenheit to Celsius. You know, when you go from Celsius to Fahrenheit, from Fahrenheit to Celsius, you have to multiply by 9/5 or 5/9. Okay, that's part of the conversion. Then you got to subtract 32 or add 32, and it's kind of a pain in the neck. But anyways, the conversion factor 9/5 or 5/9 is kind of like G, capital G. And that is because the force has to be kilogram meter per second squared. It has to be newtons in the metric system. But my numerator, if my numerator is just m1 times m2, that's kilograms squared in the numerator. My denominator is just meter squared, because that's the square of a distance. So kilogram squared per meter squared, that's not a Newton. So to get a Newton, you multiply by G. And its value, I believe, is 6.67 times 10 to the minus 11 in the metric system. And that'll convert you. But the main thing is that in fact, the most important thing about this equation is that the distance dependence is inverse r squared. Go ahead and write that down. Inverse r squared dependence. The calculus behind that would choke a mule. If mules could do calculus, the calculus of inverse r squared forces would choke that mule. It's In other words, what I'm saying is it's very difficult for grad students to grab it. But it's a fairly simple formula. It's an eyeball. And I can tell you this. Because it is 1 over r squared, it means that the gravitational force has infinite range. It is an infinite range force. That means your left earlobe is gravitationally interacting with the Andromeda galaxy, many, many light years away. The nearest spiral galaxy to our galaxy is the Andromeda galaxy. In fact, your entire body is interacting with it. Now, it's so far away that you're not getting a lot of newtons, but theoretically, this formula, anything with r squared in the denominator for the force law, infinite range. The other force of nature that is infinite range is electromagnetism. We'll talk more about that later, but I want to do an example of how NASA uses the law of universal gravitation. So let's think of NASA working with a spacecraft up in space, and here my blue dashed line is the position vector for my spacecraft. This blue set of polygons up here is the spacecraft, and it has some mass m subscript s, and then down here in the lower left corner is the Earth itself. I'm showing a quarter of the Earth. And Earth's mass, we're going to use the symbol capital M. Now, if you want to know what the mass of the Earth is, it's 6 times 10 to the 24 kilograms. And my wonderful students, that is a lot of kilograms. And you are a teeny fraction of that. Orlando is everything in Orlando. The state of Florida, if you could kind of chisel it out of the earth, the state of Florida is a teeny fraction of this. All right? But anyways, that's the mass of the earth. Okay? So now let me work on this example. So for example, you're working down at Mission Control in Houston, and you're trying to sort out and design the orbit. And if you're trying to set the distance, you also have to know, how fast it has to move on that orbit. And then you have to give big enough rockets to get it up to that orbit. Because if you use too small of a rocket, it's not going to get high enough. If you use too much of a rocket, you'll be wasting a lot of expensive technology. So they want to know exactly how big to build the rockets to do the job and have a little bit of safety factor to spare. All right, so they'll figure out any orbit, an elliptical orbit or a circular orbit. Let's work with a circular orbit, because if it is a circular orbit, we can use right down the line Sir Isaac Newton's centripetal force formula, as well as the gravitational formula. And here they are. All right, on the left is the law of universal gravitation. G times capital M times m subscript s divided by r squared. On the right is centripetal acceleration for the spacecraft, Deborah, of mass m subscript s. Okay, so that's on the right side. Right? So go ahead and emphasize. And let me emphasize this, that there's nothing essentially gravitational about a centripetal force. You can have a centripetal force for any circular path, on a tabletop, a racetrack, the Nardo Ring, anything. If it's horizontal, you don't need to factor in the gravitational force. But you can still have a horizontal centripetal force, and you use this formula for it. Now, anybody notice anything interesting about this equation, or that might help you streamline things or simplify things? What do you notice? I cannot hear what you just said. Yeah, so that's what I'm trying to say. This we derived this independently of the gravitational law. If we're on a circular orbit around the Earth, we can connect the two separate things independently. Yeah, so that is v squared over r. That is the centripetal acceleration. Notice anything about the algebra of this? Don't look at me. Look at that. We got a guy up here in the fourth row looking right at me. There's another girl asleep. No, you're not asleep. Okay, good. Well, how about this? How about we cancel ms from both sides? We could do that. And it's kind of cool because that simplifies the formula. The only mass in the formula now is the mass of the Earth. So what we're doing actually applies to any spacecraft within reason. Any spacecraft. You know, whether it's the size of a basketball or the size of a school bus or anywhere in between. Now, we can clean this up and simplify it a little bit. There's r's on both sides. So let me simplify that, and I'll actually move it up here. Here's the cleanup. I've got all the r's on the left and the v's. Let's see if I get my cursor over here. Okay, here's the r in the denominator on the left side, and here's v squared on the right. Now, what that does is it allows you to either set the r and then calculate v, or set the v and figure out what the r has to be for a circular orbit. So, for instance, in item 8, if you know the radius r of the orbit that you need for your spacecraft, you can then figure out the required speed and design your rockets appropriately so that so when you get up to that altitude, you've got the right amount of speed. Okay? Because it's all controlled by this one equation. Now, you may think to yourself, Dr. B, when does NASA ever care about that? Well, I'll tell you, they care about it if they're trying to build a satellite that orbits low enough to keep an eye on the Russians. We don't only want to read their license plates, we want to read their credit cards. We want to read the serial number on their iClicker. Keep an eye on those buzzards over there in Russia. They're always up to something. So yeah, a spy satellite, you have to have the right altitude, and that controls what the speed is going to be. And so that's something that we've got buku spy satellites doing, and weather satellites too. I mean, you would make the same calculation for something like a weather satellite. Question, Colin. There were r's on both sides. There was v squared over r on the right side, and there was an r squared in the denominator on the left side. I cross multiplied the r from the right side over to the left, and then they canceled. R canceled one of the r squareds. All right. Now, here's a second example. Okay. Say that you have a need for a certain orbital speed. In other words, you want that thing buzzing overhead, not at a specific height, but at a specific speed. All right. This equation allows you to figure that out. You put in your v and you figure out r. Now, we're not going to do that, but the guys down at, it's not that hard, but the guys down at NASA at Mission Control do this all the time. And here's one very famous application of that. Figure out the orbital distance r for a satellite that's fast enough to orbit Earth once per day. Now, can you think of a satellite? What kind of a what would that be helpful for? What would that, a satellite that orbits Earth once per day, what would that? Colin says keep track of time. You know, I've never thought about that, but actually that may be a function of the answer that I have built in here. So we'll keep that in reserve. That's a good thing. I'll have to check that out. Keep it track, because they do that with satellites. You know, The GPS that you use for your cell phone, boy, they got to know time down to the nanosecond on those babies. There's another application. Satellites that orbit once per day. What do you? TV and radio. Yeah, these are the geosynchronous satellites that you use for DirecTV, Dish Network. When you talk on long distance telephone to somebody, and like there's a minute, or not a minute, a second delay. You say something, and you got to wait for them to reply for just a second. That's because they're bouncing the conversation of a satellite, somewhere over Peru or something like that, and then back down to the Earth, out in California. And it's cheaper to do that than to send it through copper wires between here and California, apparently. So yeah, geosynchronous communication satellites, so radio and TV. Huge amount of stuff goes through these geosynchronous satellites, and they're way high up there. It's a very high orbit. Question? Centrifugal force? Did you say centrifugal? Caitlin, get down here and bounce this guy out of my... She's my bouncer back by the back door. Don't cross me. Don't cross Caitlin especially. No centrifugal force. It's on there. There's other things affecting the moon. It's not simply that. There's tides. The tides of Earth and the tides on the moon actually are synchronized now. And so that actually does slow the moon down a little bit. But if everything were perfectly rigid, like two BBs in space, then yeah, it would just be that. You wouldn't. It would just be the circular orbit. And in truth, it's the moon's orbit. Matter of fact, this supermoon eclipse we had the other day was because the moon is actually not a true circular orbit. It's slightly elliptical, and it's slightly closer during some eclipses, which is like what we had the other night. And so it's measurable, but it's really close to a perfect circle. And for most purposes, it doesn't have any slowdown or spiraling in or anything. But if it was a little bit closer, the rings of Saturn, we think, are stuff that have spiraled in and detonated basically by tidal forces. So, okay. Now let's keep going. I want to talk about this astronaut and this spacecraft. We know that according to Galileo and Newton, they're in contact. So this is a picture of an astronaut that's pushed a spacecraft, a very, very small spacecraft, off to the right. And the spacecraft is going to give him a push to the left. We know that by Newton's third law. The interaction forces are the same size, although opposite directions. And the contact time, of course, by definition is the same for both. And because that is true, the product of interaction force times interaction time must be equal if you include the minus signs. Okay, so here's a vector statement. The force, let me see if I can do this carefully. The force on the human times the interaction time, delta t, is equal to the force on the satellite, reverse the direction, the minus sign, times the interaction time, delta t. Okay? And so this minus sign here indicates that the direction of the force on the human is opposite of the force on the spacecraft. Okay? Now, that's like saying equals times equals are equal. That sounds like geometry class. All right? And that's definitely true. Now, Sir Isaac Newton says F equals ma. If you have an F, you got an ma. Here it is. The mass on the... Oops. There it is. The mass, the force on the human is equal to the mass of the human times the acceleration of the human. Same thing over here for the mass of the spacecraft and the acceleration of the spacecraft. Now, each acceleration is delta V over delta T. So delta V for the human divided by interaction time, delta T. And then delta V for the spacecraft divided by delta T over here for the spacecraft. Now, anything interesting you note there in that equation? What do you see? Delta T's cancel out, so we're going to cancel those out in a second. All right. Now, and I'm sorry, I'm a little bit out of sequence here. The equation that we should have is m times delta V for the human, mh times delta VH equals minus m for the spacecraft times delta V for the spacecraft. It's going to show up here in a second, but it's out of sync right now. So that quantity m delta V defines change in momentum if you define momentum in this way. Customary symbol for momentum is P, and the formula is simply m times V. Vectorized, it's just, you can have a scalar version or a vector version. Delta P would be m times V2 times minus V1, because that's what delta V is. Scalar and then full vector version would be vector vector V2 minus vector V1 times m, the mass of the object that you're working with. All right. Now, m is a scalar and a constant. If you're on a rocket system, the mass is always changing because you lose a lot of your rocket fuel, or you lose all your rocket fuel out the back when the rocket motor is burning. And that makes what the guys at Houston Mission Control do very, very difficult. But for us, fixed mass, constant. So here's the, oh boy. Let me get it again. All right. Here's the equation. Delta P subscript H equals minus delta P subscript S. And so that's like saying in English that the momentum exchange, delta P, for the human has to be equal but opposite to the momentum exchange for the spacecraft. All right, delta P's. And that, my wonderful students, is the thing in an interaction that is equal. The interaction forces are equal but opposite, and delta P is equal but opposite. Delta V is not, final V is not, but delta P is definitely equal but opposite. Now, last minute, I want to give you one more concept, and that is the concept of F delta T. It's known as the impulse. And here's the equation for it. This is basically Newton's second law, written in terms of momentum. F times delta T is equal to delta P. Now, I'm going to give you some problems inside web courses for homework tonight about the change of momentum, the impulse. And I'll give you some cinchy questions and work you up to some trickier questions. And that homework will be ready by lunchtime tomorrow, if not sooner, and due on Tuesday. And that concludes lecture for today. Office hours in about 10 minutes over in my office. You are dismissed. 1:14.